At 9:42 a.m., July 11, 1943, the morning sky over Sicily shimmered with rising heat. Captain Robert Bob Foster pushed his P-47C Thunderbolt into a steep climb, the massive Pratt & Whitney R2800 engine thundering beneath him. The aircraft vibrated as it clawed upward through the haze, sunlight flashing off its silver skin. But inside the cockpit, one gauge refused to stay calm. The temperature needle, climbing, red line, approaching. Foster glanced down, oil temp spiking past 115 degrees, cylinder heads pushing into the danger zone. A few more minutes and the engine would seize. It wasn't the first time. Every Thunderbolt pilot knew this feeling. The creeping dread of overheating during a climb, the smell of hot metal, the subtle shift in engine tone that told you something inside was suffering. Below him, dust from the advancing Allied invasion blew across the coastline. Above him, German radar had already detected American fighters inbound, and somewhere out there, Focke-Wulf 190s were climbing to intercept. Foster eased the throttle to save the engine, but he knew the truth. If he lost too much power now, he'd never reach altitude before the Luftwaffe arrived. And so began the crisis that forced engineers to reconsider a strange, rejected idea, one that would soon make the P-47 almost impossible to overheat. In 1942, as the United States entered full-scale war on two continents, American air strategy depended on a single promise: fighter power would reach farther, climb higher, and hit harder than anything the Axis could put in the sky. But behind the scenes, that promise was cracking. The Republic P-47, a Thunderbolt, America's new heavyweight fighter, was supposed to be the answer. A giant of an aircraft, an airframe built around the massive Pratt & Whitney R2800 double Wasp engine and a turbo supercharger system unlike anything used before on a frontline fighter. On paper, it was unstoppable. In reality, it was overheating. Early testing at Mitchell Field, Farmingdale and Wright Field all revealed the same demon: excessive heat build-up during long climbs and combat power settings. Pilots reported oil temperatures rising too quickly, cylinder heads reaching critical levels, and engines that, under wartime stress, ran closer to the edge than engineers ever intended. The cause was obvious but unsolved. The R2800 produced extraordinary power, but it also produced extraordinary heat. The Thunderbolt system of ducts, intercoolers, cowl flaps, and rear-mounted turbo plumbing created airflow complexities no engineer had fully mastered. Engineers knew the aircraft could perform, but they also knew the margin between safe operating temperature and catastrophic failure was far too thin. Meanwhile, the war situation made the problem even sharper. By late 1942, the USAAF desperately needed reliable escort fighters over Europe. German Jagdgeschwader were tearing into unescorted B-17 and B-24 bomber streams. Losses were mounting. Commanders demanded that the new P-47 units begin operations immediately, even if the aircraft wasn't fully ironed out. At the same time, in the Pacific, long-range missions from New Guinea and the Solomon Islands pushed engines to their limit under brutal tropical heat and humidity. Every climb to altitude became a gamble. Every escort mission felt like a test flight. Ground crews were overworking engines, pilots were nursing throttles, and commanders were losing faith. It was a situation so widespread, so persistent, that many believed the Thunderbolt's cooling issues were simply part of its personality, a flaw to be endured, not fixed. But deep inside Republic Aviation's engineering offices, one man refused to accept that answer, and the pressure on him was only beginning to build. The deeper engineers dug into the Thunderbolt's design, the clearer the problem became. Heat was being trapped where it shouldn't be, and wasted where it shouldn't be lost. The P-47's enormous turbo supercharger, mounted far behind the cockpit, forced long ducts ducts to carry compressed air through intercoolers and back into the engine. It was an engineering masterpiece, but also a nightmare. Every turn, every bend, every inch of ducting created turbulence, pressure drops, and unpredictable thermal behavior. The aircraft didn't just run hot, it ran unevenly hot. At high power settings, the R2800 produced so much heat that the cowl flaps, designed to let excess heat escape, couldn't keep up unless opened wide, but opening them too far created drag. Drag killed climb performance. Losing climb performance meant losing altitude advantage. Losing altitude advantage meant German fighters dictating the fight. It was a trade-off pilots despised. Field units tried everything. Some trimmed cowl flaps, some altered oil cooler doors, some experimented with quick fixes using sheet metal and improvised vent plates. Nothing worked consistently. Different airfields reported different temperature behaviors, leading many to believe the problem wasn't a single flaw, but a combination of dozens. Republic Aviation's engineering teams were frustrated. Right field evaluators were impatient. Pilots were blunt. A fighter that overheated during a combat climb wasn't a fighter. It was a liability. Worse, the USAAF was comparing it to the P-51 Mustang, which, once paired with the Packard Merlin engine, seemed poised to take the spotlight. Funding, manufacturing orders, and political favor all depended on the Thunderbolt proving itself. Anything that hinted at chronic issues threatened the program. Internally, meetings grew tense. Some engineers argued for redesigning the cowl structure entirely. Others insisted the turbo supercharger's airflow routing needed an overhaul. A few simply said the aircraft was too big, too complex, and too late to fix. That was the environment into which one quiet engineer stepped forward with a different idea. An idea that didn't require a redesign, didn't require major manufacturing changes, and didn't require scrapping the system. It required only a small, counterintuitive change to how the Thunderbolt breathed. But before anyone would trust it, they needed to trust the man who proposed it. And his story began long before the overheating crisis ever reached its tipping point. He wasn't a pilot, he wasn't a commander, and he never fired a machine gun in combat. But in the summer of 1942, in a small drafting room at Republic Aviation's Farmingdale plant, engineer Edward "Ed" Nance was fighting a war every bit as critical as the one raging across the oceans. Nance was not the kind of man who drew attention. He was bookish, quiet, analytical. A slide rule always hung from his belt, and he carried notebooks filled with precise sketches, airflow diagrams, and thermodynamic equations. While others debated, he observed. While others speculated, he measured. It was said that he could detect a temperature pattern by sight alone. Watching heat distort metal surfaces or the way exhaust shimmered as it left the cowling. Born in 1910 in Illinois, Nance studied mechanical engineering at Purdue University before joining Republic Aviation in the late 1930s. He arrived when the company was still small, before America entered the war, before the Thunderbolt existed as more than scattered drawings pinned to drafting boards. His early work focused on airflow behavior, specifically how air moved through tight engine compartments under stress. When war broke out, everything changed. Republic's workforce exploded, the pace tripled. Engineering offices became war factories of their own, producing designs faster than they could refine them. Nance found himself caught in the storm, responsible for thermal behavior inside a fighter, unlike anything the US had ever attempted. The P-47 was meant to be a masterpiece of power and engineering. But Nance saw what few others noticed. Its strength was also its weakness. The engine produced unmatched horsepower, but the surrounding airflow system was so intricate that even tiny inefficiencies multiplied under combat power. The slightest disruption, the wrong angle on a cowl flap, a poorly tuned duct, a misaligned intercooler door, could send temperatures soaring. As units in Europe and the Pacific reported overheating problems, the pressure on Nance increased. He worked long evenings poring over pilot reports, maintenance logs, and internal temperature readings. He reviewed data that others dismissed as noise, tiny spikes in oil temperatures during high G turns, unpredictable fluctuations when the cowl flaps shifted at altitude, inconsistent cooling between squadron aircraft. The more he studied, the more convinced he became that the problem wasn't the engine itself. It was how the Thunderbolt breathed. Nance had no ego about the aircraft. He didn't defend it blindly, nor did he attack it for flaws. Instead, he approached it like a living system, believing that if he could understand the airflow's behavior, he could control its temperature. Yet this perspective isolated him. Many engineers focused on structural solutions, bigger openings, larger ducts, more airflow. Nance believed the opposite. Bigger wasn't better. Smarter was better. Precision was better. He wasn't universally liked for that. Some colleagues thought he was overthinking things. Some test pilots thought he didn't understand real combat conditions. Some managers thought his ideas were distractions from the urgent need to get fighters into the field. But Nance wasn't trying to win arguments. He was trying to prevent engines from failing, because every failure meant a pilot falling from the sky. And as overheating failures worsened, he began developing a strange, counterintuitive idea, one that violated conventional thinking and one that his peers would soon call impractical, unnecessary, and even dangerous. But before that conflict began, the world needed to understand the mind behind the idea. For Edward Nance, engineering was never about prestige. It was about patterns, subtle clues hidden in numbers, airflow currents, metal temperatures, and the lived experience of pilots who trusted their machines with their lives. And it was those patterns, small and easily ignored, that shaped the way he approached every challenge inside the Thunderbolt. He spent hours on the flight line, kneeling beside hot engines, while crew chiefs wiped oil from their forearms. He asked pilots what they felt, not just what the gauges said, how the engine sounded during a climb, whether the throttle felt heavier under strain, whether the air inside the cockpit shifted when the cowl flaps changed position. Many engineers relied on test stands and wind tunnels. Nance relied on the men who flew the aircraft into combat. He listened, he catalogued. And he noticed something everyone else seemed to overlook. Overheating wasn't uniform. Some aircraft ran hotter than others, some units saw almost no issues, others saw rising temperatures every time they climbed above 20,000 feet. The same model P-47 could behave differently from field to field, pilot to pilot, mission to mission. To Nance, this inconsistency said one thing. The system wasn't flawed, its airflow was misunderstood. He began obsessively sketching airflow diagrams, blue pencil lines representing the cold incoming air, red lines tracing the hot, turbulent exhaust currents, hatch marks showing pressure zones around the intercooler and oil coolers. Over time, those sketches turned into theories, and those theories into something more dangerous, questions. Why did the cowl flaps work better at certain angles than others? Why did temperatures spike during high-angle climbs but stabilize during dives, even when power settings were similar? Why did opening the flaps wider sometimes worsen temperatures instead of improving them? Senior engineers dismissed these questions. Pilots said they only wanted the overheating fixed, no experiments, no risky modifications. Managers insisted that production could not slow for non-critical redesigns. But Nance continued pushing because the data refused to stay quiet. He also carried something others didn't, a sense of debt. Early in the war, he had watched a test pilot nearly lose an engine during a climb-out demonstration. The pilot survived, but the moment stayed with Nance. He never forgot the sound of the engine laboring as temperatures spiked, the mechanical groan that preceded a potential failure. He later admitted privately that every overheating incident felt personal. As long as P-47s were struggling, he felt he had personally failed the men flying them. This emotion, rare for an engineer, kept him working long after others went home. He studied airflow behavior late into the night, refining an idea that he wasn't yet ready to share. It wasn't entirely his invention. Instead, it emerged from observing countless small details others dismissed as random. But when he finally shaped the idea into its final form, simple, precise, and strange, he knew what the response would be. It contradicted engineering dogma. It required pilots to do something they had been taught never to do. It seemed counterintuitive, almost reckless. And when he presented it, the reaction would be as cold as the airflow he was trying to control. Because this was the birth of the idea that would soon be mocked, rejected, and almost banned, long before it proved itself in the chaos of combat. The idea came to Nance, not in a drafting room, but while standing on the edge of a runway at Westover Field, watching a maintenance crew warm up a P-47's engine. The pilot cycled the throttle, opening and closing the cowl flaps in quick bursts. Every time the flaps snapped wide, a burst of hot air blasted out, and the temperature needle jumped higher instead of dropping. Most engineers blamed this on workload, or pilot technique, or instrument lag. Nance didn't. He saw something else. The cowl flaps were disrupting the airflow rather than helping it. The Thunderbolt's cooling system depended on smooth, high-velocity air passing through the engine, an oil cooler. But when pilots opened the flaps too wide, standard procedure during overheating, the flaps actually caused turbulent pockets, slowing the airflow and trapping heat inside the cowling. In other words, the pilots were doing exactly what the manual said, and making the problem worse. Nance's idea was shockingly simple. Instead of opening the cowl flaps wide during overheating, pilots should partially close them to a narrow, controlled angle that preserved airflow velocity while still releasing heat. A smaller opening, less drag, more airflow speed, lower temperatures. It contradicted everything pilots were taught. It contradicted decades of aviation cooling logic. And worst of all, it required changing pilot behavior, the most rigid rule in wartime aviation. To most engineers, it sounded backward. To Nance, it was physics. But the moment he wrote the proposal and sent it up the chain of command, he knew what was coming. Skepticism, resistance, even anger. Because asking pilots to close cowl flaps during overheating seemed not just strange, but dangerous. The reaction inside Republic Aviation was immediate and brutal. Senior engineers dismissed Nance's proposal almost before they finished reading it. Closing cowl flaps during overheating, reducing the opening when temperatures were rising. It was the opposite of everything pilots had been trained to do since the dawn of air-cooled engines. One test crew chief reportedly muttered, "Next he'll tell us engines run cooler with less oil." Some thought Nance misunderstood the problem. Others believed he was misreading the data. A few said outright that his idea was too risky to even test. At Wright Field, evaluators were even harsher. The Thunderbolt program was under pressure, and officials viewed unconventional suggestions as distractions. They wanted solutions that were simple, predictable, and in line with established doctrine. Nance's idea was none of those things. The Office of Flying Safety went further, warning that telling pilots to partially close cowl flaps during overheating could cause engine failure, fire, or loss of aircraft. Their stance was clear. The idea wasn't just unorthodox, it was potentially dangerous. Test pilots themselves were divided. Some refused to even try it. Others laughed at the suggestion, saying it was engineering theory with no place in a cockpit. To them, wide-open flaps were a survival instinct. Changing that instinct in combat felt reckless. The idea was formally rejected, informally mocked. quietly buried. Nance returned to his desk, frustrated but not defeated. He knew the airflow patterns were real, he knew the data made sense, and he knew, because he had stood next to hot engines and watched the airflow misbehave, that his idea could work. But no one would listen until the day the war forced their hand. And that moment was coming faster than anyone expected. By early in 1943, the Thunderbolt was finally entering large-scale combat. The 4th, 56th and 78th Fighter Groups in England were preparing for deep penetration missions over occupied Europe. These operations demanded long climbs, long hot climbs, into thin air where Luftwaffe fighters waited. And that was the problem. The moment P-47s began their ascent, from airfields like Debden, King's Cliff and Boxted, temperatures started creeping upward. Pilots pushed their throttles forward, engines roaring, turbo superchargers glowing cherry red. Within minutes, oil temperatures edged into the danger zone. Cylinder heads flirted with redline. Every man in the cockpit knew the feeling, sweat on the palms, heat building under the instrument panel, the hope that the gauge would stop climbing before something catastrophic happened. Down below, ground crews were worried too. They had seen what happened to engines that ran too hot, scored cylinders, burned oil, warped baffles. A single mission could undo hundreds of hours of careful tuning, maintenance logs filled with warnings, running hot during climb, temperature spike at $22,000 feet. Consider reducing power on ascent. But reducing power meant losing altitude meant losing the fight. And German pilots in their Bf-109Gs and FW-190As were exploiting the issue. They waited high above bomber streams, diving the moment P-47 formations appeared. Knowing that American Thunderbolts often reached the battle already at their engine limits, reports flowed in from every group. Engines struggling above 25,000 LFT, cannot maintain climb rate without overheating, forced to level off early. High command demanded answers. Engineering teams were dispatched to combat groups. New maintenance procedures were tested. Updated manuals were issued. But nothing worked consistently. The hotter the missions became, the worse the problem grew. And as summer operations intensified over Europe and the Mediterranean, the USAAF was approaching a breaking point, one that would force someone, somewhere, to try something new. Something that had already been rejected. June and July 1943 pushed the Thunderbolt harder than ever before. The Allies were preparing for Operation Husky, the invasion of Sicily, and fighter groups from England to North Africa were flying longer, hotter missions under heavier loads. Every climb out felt like a test of mechanical endurance. In the Mediterranean, heat radiated off the runways before noon. Engines baked even before ignition. Pilots of the 325th and 382nd Fighter Groups described the same ritual. Start the engine, watch the needle climb, pray it stabilized. But the moment they lifted off and pointed their P-47s upward, temperatures surged again. Oil thinned in the heat, airflow thickened with dust, and the tightly packed ducts inside the Thunderbolt struggled to keep up. In England, the air was cooler, but missions were longer. Escorting bombers toward the Ruhr or along the French coast meant sustained climbs to 25,000 or 30,000 feet. The very altitude the P-47 needed to dominate the fight was the altitude where its thermal limits were most dangerous. Commanders hated the trade-offs. Open the cowl flaps wide, temperatures dropped slightly but drag increased, crippling climb performance. Close them too far, the needle shot upward like a warning flare. Pilots were stuck in a narrow band between overheating and becoming slow, vulnerable targets. And then came the worst scenario. Multiple groups reporting near-simultaneous overheating failures during a large escort sweep in late June. Engines lost power. 2 aircraft aborted the mission. 1 pilot barely made it back, gliding in with an engine that seized on touchdown. For High Command, this wasn't just a maintenance headache, it was a strategic threat. The Luftwaffe still held the advantage over Europe. Every failed fighter climb weakened bomber protection. Every overheated engine meant a gap in the escort screen. Something had to change, something simple, something immediate. And for the first time, squadron leadership became willing to consider ideas they had previously dismissed, even the strange, counterintuitive one that had been rejected months before. The stage for the crisis was set. All it needed was the moment when overheating pushed pilots to the edge and forced them to try the idea no one trusted. The moment came on July 11, 1943, the same mission Captain Robert "Bob" Foster climbed into that rising Sicilian heat. It was supposed to be a routine cover patrol for the advancing Allied forces below. A straightforward climb to altitude, then a sweeping arc over the coastline to deter German fighters heading toward the beaches. But nothing about that morning was routine. From the moment Foster pushed the throttle forward, he felt the Thunderbolt strain. The R-2800 roared, the turbos spun up, and the airframe trembled as heat built beneath the cowling. He glanced at the temperature gauge. It was already climbing faster than usual, faster than he wanted to admit. Behind him, his wingman radioed the same warning. "She's running warm, Bob." The formation lifted off the dust-blown strip, engines shimmering in the morning haze. As the P-47s began their climb toward the intercept altitude, the temperature needles marched upward, steady, relentless, unforgiving. At 8,000 feet, the line was yellow. At 12,000 feet, the edges of the gauge began to glow in the cockpit sunlight. By 16,000 feet, Foster could smell it, the faint metallic odor of an engine pushed too far. The rest of the squadron was feeling it too. One pilot cracked his cowl flaps fully open, hoping to cool the cylinder heads. Instead, the moment he did, his climb rate dropped sharply. The sudden drag slowed him, pulling him out of formation. His voice crackled through the radio, strained, frustrated, losing power, temps still rising. Damn it! He was forced to level off, unable to climb any higher without risking total failure. But the mission had to continue. The Luftwaffe was already climbing from the north. The P-47s couldn't afford to meet them low. They needed altitude, needed the advantage their aircraft was built to deliver. Foster pressed on, watching the gauge cross into the red. He eased the throttle slightly, hoping to buy a few minutes. Instead, the needle ticked even higher. Turbulence over the ridgeline disrupted airflow just enough to worsen the rising heat. And then the worst happened. His engine coughed, a single, violent cough, like a giant exhaling under strain. The entire airframe shuddered. The oil temperature surged past the red line. If the R-2800 seized now, he wouldn't have altitude to glide to safety. Below him was rocky terrain, no flat land, no margin. Another pilot wasn't so lucky. Lieutenant Carey radioed abruptly. "I'm losing oil pressure, engines shaking hard. I think she's about to—" His voice cut out. His engine seized seconds later. The propeller windmilled as he bailed out over hostile terrain, drifting toward the jagged Sicilian hills. Foster didn't have time to mourn. Radar warnings came through command channels. Focke-Wulf 190s, fast, climbing, deadly, were approaching from the northeast. The P-47 squadron was in the worst possible situation. Overheating engines, climbing too slowly, losing formation integrity, and about to be attacked from above. The radio filled with overlapping voices. "Temps critical. Need to back off. Can't hold climb. Bob, we have to level—" Foster knew the truth. Leveling off meant surrendering altitude. Surrendering altitude meant dying, but climbing meant cooking the engines alive. He looked at the gauge again. The needle was buried in the red arc. The cockpit felt hotter. The engine tone shifted, a deeper, more troubled vibration that pilots recognized immediately, the warning before failure. Panic flickered in his chest, not fear of the enemy, but fear of mechanical betrayal. An engine failure here would mean bailing out near German positions or crashing into unforgiving ground. He reached for the cowl flap control, instinctively ready to yank it wide open like every manual instructed. And then he stopped. A memory flashed, something he'd heard weeks ago. A conversation among ground crew at Boxted, an engineer's idea, ridiculed, dismissed, laughed at, something about airflow, something about smaller openings, something that didn't make sense. Foster hesitated, hand hovering over the control. Every instinct screamed not to do it, every manual warned against it, but every second he waited pushed the engine closer to the point of no return. Above him, German fighters moved into attack position. Behind him, half his squadron was overheating. In front of him, the mission and the survival of everyone around him depended on finding a miracle. He exhaled once, steadying his hand. And he did the unthinkable. He partially closed the cowl flaps. The moment Captain Foster eased the cowl flaps closed, not open, not wide, but to a narrow, deliberate angle, the effect was almost immediate. At first, nothing happened. The temperature needle held steady in the red, quivering at the edge of disaster. The engine still vibrated with the tension of impending failure. Foster kept climbing, jaw clenched, waiting for the blowout he was sure might come. Then, 10 seconds later, the needle twitched, barely, almost too small to notice. 5 seconds more, and it twitched again, this time downward. Foster blinked hard, thinking it was a trick of the light. But the metal smell in the cockpit faded slightly. The engine tone shifted from strained to stable, and the temperature, unbelievably, continued dropping. 115 to 112, 180. It was working. The airflow, now funneled through a narrower opening, accelerated through the cowling instead of stalling inside it. Smooth, laminar flow replaced the turbulence that had been trapping heat. The intercooler received cleaner air. The oil cooler shed heat more efficiently. The R-2800 stopped suffocating. Foster could feel the Thunderbolt breathe again. He keyed his radio. "Close your flaps. Partway. Not open. Close them down." At first, stunned silence. Then a skeptical voice. "Bob, that'll kill the engine. It's dropping temps. Do it." One by one, the men tried it. Against instinct, against training, against every manual they'd ever read. And one by one, their needles began to fall. 23 squadrons' climb rate stabilized, their formation tightened, their engines smoothed out. The chaotic chorus of overheating warnings faded into static. Then came the enemy. A group of FW-190s dove from above, confident they were attacking a vulnerable American formation struggling uphill. But instead of scattered overheating fighters, they found a wall of P-47s now climbing with renewed power, cooling stabilized, throttles back to combat setting, engines roaring with full strength. Foster rolled into the attack. With the cowl flaps now set to that perfect sliver of opening, the Thunderbolt retained the climb performance that made it such a dangerous opponent at altitude. A German fighter overshot. Foster fired a burst. Tracers arced upward, stitching across the FW-190's left wing. The aircraft snapped into a dive trailing smoke. Other P-47s followed. No engines failed, no power losses, no forced level-offs. For the first time that day, the Americans held the altitude advantage. The Luftwaffe pilots, realizing their mistake, disengaged and disappeared into cloud cover, unwilling to face thunderbolts that weren't limping along with overheating engines. When the skies finally cleared and the squadron regrouped, Foster looked at his temperature gauge, holding steady, cool, almost calm. The rejected idea had saved the mission, saved the engines, saved the pilots. And that day, a quiet engineer's counterintuitive solution, mocked, dismissed, nearly banned, proved itself in the only environment that mattered, combat. But the results would not remain confined to one mission. Word spread quickly, from pilot to pilot, squadron to squadron, base to base. The Thunderbolt community wanted to know why the trick worked. They wanted to know who had suggested it. They wanted to know how such a simple change could have avoided months of overheating struggles. And soon, that interest would force the USAF to acknowledge what had happened in the Sicilian sky. When Captain Foster's squadron landed that afternoon, the ground crews expected the usual aftermath of a high-power climb in Mediterranean heat: scorched oil, burned plugs, blistered baffles, and at least one engine needing replacement. Instead, they found something else entirely. Temperatures were normal, oil was clean, cylinders showed none of the stress patterns they had come to fear. Within an hour, pilots from multiple flights were gathered around Foster's fighter, pointing at the cowl flaps and trying to understand how a technique that went against every manual had kept the R-2800 so cool under such brutal conditions. The reports written that night spread like wildfire. Temperature stabilized after partial closure of flaps. All aircraft maintained climb, no engine failures. Enemy intercepted with full power available. For squadrons battered by weeks of overheating, it was a revelation. Word moved up the chain quickly. By the third day, pilots in the 57th and 86th fighter groups were testing the technique. By the 7th day, units in England, 4th, 56th, 78th groups, received urgent telegrams describing the process. Close flaps to narrow opening during high-temp climb, increases airflow velocity, reduces overheating. Results came back almost immediately. In 1 week, 18 overheating incidents dropped to 3. In 2 weeks, engine-related mission aborts fell by more than 70%. In a single month, over 40 aircraft reported maintaining full climb power with no temperature excursions above limits. Commanders could hardly believe the numbers. The Thunderbolt's biggest reliability weakness was collapsing, not with a redesign, not with new parts, but with a pilot technique that cost nothing and required no modification to the aircraft. Maintenance chiefs reported dramatic reductions in blown cylinders and warped baffles. Engine shops saw fewer replacements and fewer emergency teardowns. Statistically, the trick preserved dozens of engines across multiple groups. Pilots gained something even more important: confidence. Climbs that once felt like mechanical torture tests became predictable, manageable, almost routine. For the first time, squadrons could commit to high-altitude intercepts without fearing that half their fighters would overheat before reaching combat. And that shift had consequences. More missions were completed, fewer aircraft aborted, more fighters reached altitude ahead of Luftwaffe interceptors, more bomber formations survived. No one could argue with the numbers. The USAF, however, faced an uncomfortable truth. A solution they had rejected, an idea they had dismissed as confused, illogical, and even dangerous, was suddenly spreading with undeniable success. They needed to investigate, they needed to verify, but most of all, they needed to acknowledge the engineer whose rejected idea had just transformed the most powerful fighter in their arsenal into a machine that finally lived up to its potential. The Air Force could no longer ignore the trick, and the man behind it was finally being called forward. In the weeks that followed, what began as a desperate field improvisation in the skies over Sicily evolved into a formal investigation. Right field analysts requested temperature logs, climb reports, and testimonies from pilots across multiple theaters. Maintenance chiefs submitted engine teardown data showing drastically reduced thermal damage. Even skeptical test pilots grudgingly admitted the impossible. Closing the flaps had cooled the engines more effectively than opening them. It didn't take long for engineers to trace the effect back to the airflow behavior Edward Nance had mapped months earlier. His diagrams, once ignored and quietly pushed aside, were now being studied by senior officers, aerodynamicists, and the very same engineers who had rejected them. When Nance was summoned to Wright Field for a technical debrief, he arrived expecting more resistance. Instead, he found a room full of officers and engineers waiting to hear precisely how he had figured it out. They listened to his explanation of airflow velocity, turbulent versus laminar cooling, and the pressure relationship inside the Thunderbolt's cowl. They studied the equations, the sketches, the experimental notes he had sketched late at night when no one else believed him. For the first time, his idea wasn't being brushed aside. It was being taken seriously. Within a month, an official USAF technical bulletin was issued. During high-power climbs and overheating conditions, pilots are instructed to adjust cowl flaps to a controlled, partially closed position to maximize airflow velocity and cooling efficiency. This single line, simple, unadorned, almost mundane, quietly rewrote the way Thunderbolts were flown. Flight instructors across England, North Africa, and the Pacific began drilling it into new pilots. Maintenance crews added it to standard operating procedures. Squadron operations officers updated climb profiles. Test flights confirmed what Foster's squadron had discovered under fire. Temperatures dropped faster, stayed stable longer, and allowed full-power climbs without excessive drag. The results were immediate. Over Europe, P-47 groups reported unprecedented reliability. Engine failures plummeted, abort rates dropped, altitude performance improved across entire formations. Thunderbolts began meeting German fighters not tired, overheated, or half-powered, but strong, cool, and ready for combat. Bomber crews noticed too. Escort screens tightened. More Thunderbolts stayed with the bombers longer. The Luftwaffe found itself facing disciplined, powerful American fighters climbing cleanly into the fight instead of struggling to maintain altitude. The effect rippled further than anyone imagined. A small, counterintuitive adjustment helped enable Thunderbolt groups to perform deeper escorts, longer sweeps, and more aggressive intercepts. It supported the expansion of long-range operations. It reduced attrition, it increased sortie rates, it saved engines, saved airframes, and, most importantly, it saved pilots. For Edward Nance, none of this fame mattered. He declined formal recognition, preferring to stay with his drafting table and airflow diagrams. But within Republic Aviation, his name circulated quietly among pilots and crew chiefs. They knew, they remembered. Letters began arriving from combat groups thanking him, some technical, some emotional. One pilot wrote, "Your idea brought me home when my engine should have quit." Another simply wrote, "Thank you for giving us our aircraft back." Nance kept every letter in a small metal box in his desk. As the war intensified in 1944, the Thunderbolt went on to become one of the most reliable, rugged, and effective fighters of the entire conflict. Its cooling problems, once a crippling weakness, faded into memory, replaced by stories of the P-47 climbing higher, diving faster, and soaking up punishment better than any other Allied fighter. Pilots trusted it with their lives, crews trusted it with their workload, commanders trusted it with their missions, and yet behind that reliability was a moment almost lost to history. A pilot in overheating trouble, a desperate decision at altitude, and a quiet engineer's strange idea that no one believed until it worked. In post-war years, when historians celebrated the P-47's legendary toughness, few remembered the small airflow adjustment that had kept its engines alive under some of the harshest conditions of the war. And fewer still knew the name of the man who saw what no one else did. But the pilots who relied on the Thunderbolt never forgot. Because for them, the difference between an engine that overheated and an engine that survived was more than engineering. It was the difference between life and death, And as one veteran pilot said decades later, a big fighter like the Jug shouldn't have needed a miracle, but it got one. The story of that miracle, of a strange, rejected technique that transformed the Thunderbolt's cooling system, was never about luck or instinct or chance. It was about one engineer who refused to accept failure. One mind that questioned what others took for granted. One idea that seemed too strange to work until it changed everything. But none of it would have happened without one man's stupid idea.